So this one could be a little confusing to most of you because it involves the log function calculation. So, but it's very important because sometimes the reliability, sometimes the hourly failure rate lambda will not be provided directly. So you have to calculate it based on the provided information. So the reliability can be modeled as this. Just remember this function right here, okay? Write it somewhere and prepare for the final exam. You can put it in your cheat sheet. So the reliability can be modeled as this. The probability of it all surviving time point t is the exponential negative lambda multiplied by the time t. Okay? And remember, the lambda is the hourly failure rate. So if you multiply by t, it's basically gives you the probability of failing in this particular time, t. Okay, so that is what it is. If you look at exercise number 4, a component has a reliability of 98% for the first 150 hours of normal use. Okay, so what you have in here is 98 equal to exponential. This is constant, okay? Negative lambda is unknown. We know time is 150. Okay, so here this thing is constant. I don't remember exactly what's the size of e exponential number. It was 2.38 or something like that. So when you model a curve like this, a lot of times we rely on the exponential e. Okay, so you have everything that is known and constant. You just need to calculate lambda. So this is a very simple question, but the challenge comes from how to obtain this lambda in order to, in terms of shifting all these components right here. So this is a brief review of log function and exponential function conversion. So if you remember, y equals e powered by x, and then your log e y is equal to x. Okay, if you forgot all of these, I recommend you to pause for a second to read through the lines and see how it goes. Okay, and because log e is a natural log, ln, so ln y equal to x. So these two are the same thing basically. Okay, natural log is equal to log of e. Okay, just remember this law here. And then the problem here is the component has a reliability of 98, first 150 hours normal usage. Please determine the hourly failure rate lambda. So here, this information was offered previously. Failure t, we need to get lambda. So, of course, I explained so far. Oh my God, how to do the next step? And don't worry and think about this, okay? And then you can do some conversion, and natural log 0.98 equal to negative lambda over 150. So you will eventually convert it into this format. And then you can rely on Excel to solve it. Okay? ln in Excel, you can enter directly ln. Do not forget, here is a little negative sign here. So negative natural log 0.98 divided by 150, and it gives you the hourly failure rate of 0.00135. Okay, so here you need to spend some time here. Okay, if you totally blew here, you kind of have to review this part. If you really have no clue about what this is, you can just skip it. You can just skip it. Okay, if I find out a lot of people have skipped this, I can make this as part of final exam. Okay, so that those who know how to solve this can get some extra credit. But anyway, I encourage you to take a look at this. I think I think this part is a bit challenging, but if you know what you're doing, you'll be fine. And lastly, last exercise here. Based on the result of exercise 4, which is lambda is this size and the formula, please find out the following. Failure rate in a 1 hour period. Okay, failure rate in 1 hour period. So this gives you survival rate. This is asking about the failure rate. So what you need to do is naturally 1 minus that, or 1 minus this function. That will give you failure rate, because this part is a survival rate. Okay, this part is a survival rate. 1 hour, 2 hour, 3 hour, 100 hour, 150 hour. How long does it take to experience the first failure, which is 1 over lambda? This one is easy. You can just do 1 over 0.000135. Okay. Yep, this is solution. Lambda is here. I'm almost seeing an end. That's why I'm laughing. So happy. So lambda is here, and 1, 2, 3, 4, 5. And you can calculate the survival rate first in this case, and then the failure rate. Okay? And in the previously, we actually calculated failure rate first based on this formula, and then we calculated survival rate based on this number. But when you use the formula, which is T, well, this gives you the survival rate right away without going through this middle step. Okay? Therefore, you will be seeing exactly the same result, even you are using different approach. Okay? Let me take some time to explain this one right here. What is this guy talking about? So E negative lambda T in Excel, what you can do is EXP. Okay, this is exponential number, and negative whatever your lambda value is, you multiply whatever your time value is. Okay, so basically this is what this is all about. Okay, so this is a summary of all the exercises we've done so far. If you look at the problem number 1, it's the most fundamental aspect to calculating failure rate lambda. And the key here is to understand the total number of hours tested. Okay, so that was a bit tricky because some models, some units will die in the middle. You don't have to calculate entire 100 hours when you're calculating the total cumulative testing hours. Okay, that was the key here. And exercise number 2, obtaining reliability function using the normal distribution, that was a piece of cake. Okay. This is to demonstrate the random nature of the failure. Sometimes we can model using normal distribution, but more commonly, when the failure is the function of time, we use exponential distribution. So obtaining the reliability function using exponential distribution. That is exercise 3, understanding characteristics exponential distribution, which is very, very important, calculating lambda from a given failure rate. Given a failure rate. In this case, failure rate was expon dist something in Excel. If you remember the curve, this is the failure rate. Okay? This is the survival rate. At point of X. Survival rate at the point of X. This is a failure rate or probability of failure in the point of X. And number 5 is calculating probability of failing using, we just finished this. 4 and 5 are somehow somewhat related. Okay, so this is it on the reliability. Next Tuesday, I'm going to demonstrating the reliability of system. Okay, reliability of system. So that is not as math intensive as this particular section. Here, it will be helpful if you understand what is called an independent event. Independent event. So probability of A given B is equal to probability of A itself. So in other words, event B doesn't interfere with event A. Okay, what I do here tonight has nothing to do with your schedule tonight. Is that right? It is not. Therefore, event B, which is when whatever one is doing now, has something to do with whatever you are doing in your own place, at least tonight. Okay? But whatever people in, let's say, Europe doing now has nothing to do with what you're doing today, which may be true because of this coronavirus, but I think you get the idea. Each event does not interfere with each other. Okay, so if you go to Walmart, if you see the customer A, whatever he buys has nothing to do with customer B, assuming these two are stranger, total stranger. Okay, and the probability doesn't interfere with each other. That's what we call it as independent event. Okay, so I think we're only going to focus on independent event because that's going to be more simple. And in the parallel system, we'll be utilizing the binomial probability distribution. So at least one unit fails given there are two units are functioning, things like that. That will be our rhetoric. And then we're going to combine both items to discuss the complex system probability, and that's what we're going to do in the final section of the reliability chapter. Okay, thank you. See you later.